So for the second problem, a consumer has an average demand of 400 kilowatts at a power factor of 0.8 lagging and annual load factor of 50%. The tariff is 50 rupees per kVA of maximum demand per annum plus 5 paise per kilowatt hour. If the power factor is improved to 95 lagging, 0.95 lagging by installing phased advancing equipment, calculate number 1, the capacity of the phase advancing equipment, and number 2, the annual savings. Now kindly add this last statement in your module. I think I failed to write this one. The phase advancing equipment costs 100 rupees per kVAR, and the annual interest and depreciation together amount to 10%. So number 1 is technically just asking for the capacity of the phase advancing equipment. So that must be the Q offered by the capacitor in kVAR. So I guess we all know how to solve that already from now. For now, the only difference would be if you're going to read from here, since the tariff is going to be based on maximum demand terms, then you should be solving everything in terms of the maximum demand. Why am I saying that? Because what is given as the power, which is 400 kilowatts, is the average demand. However, I know that you know the formula already for the load factor being the ratio of the average load to your maximum demand. So the maximum demand of real power for this must be 400 kilowatts, which is the average load, divided by your load factor, which is there 50%, 0.5. This is obviously 800 kilowatts. So in the diagram, this is the 800. Now, formerly, this is your power angle using the original power factor, which is 0.8. So inverse cosine of 0.8 must be 36.87. So this is 36.87 right here. And then it's now corrected to a new power factor, which is 0.95. So this will be inverse cosine of 0.95, which is 18.1949. There. Let me make it clear that the 0.95 there is not the optimal value of power factor. If you're going to solve for the optimal value, the y here is obviously 100 times 0.1 based from the discussion earlier, and the x is obviously 50. So 10 over 50 squared, 1 minus answer, square root of answer. It's not going to give you 0.95. Okay? So this is not the optimal power factor. So this is 18.1949. So from here, from the original angle, which is 36.87, we can solve for the original value of the Q, the reactive power. So trigonometric operations, obviously tangent, opposite over adjacent. Tangent 36.87 is Q1 over 800. So this must be 800 kilowatts. Tangent of 36.87, which is 600.0022 and the unit of this is now in kVAR. Similarly, the new value of reactive power after the correction is now 800 kilowatts. Tangent of this time 18.1949, which is 262.9477. So, what caused the change? Obviously, it's the power factor correcting equipment. So, if this is 600.0022 and this one is 262.9477, then the Q offered by the capacitor is 600.0022 minus 262.9477 must be 337 kVAR. There. So apparently this is now the rating it's talking about. So this is the capacity of the phase advancing equipment, 337.0545. Now, number 2 can be a little bit tricky. It's asking for the annual savings. So what technically happens here? After the power factor correction, we now have this smaller triangle. And you observe that the hypotenuse of the smaller triangle is smaller than the original one. The hypotenuse happens to be your kVA, your apparent power. So, cut the story short, power factor correction also decreased the kVA. And that only means one thing, savings, because since we've solved everything in maximum demand terms, the tariff is actually based on the kVA of the maximum demand. So 50 rupees per kVA. So if the kVA decreased, then the tariff also decreased. However, it's a double-edged sword because you also paid for your equipment. So there will be a savings for the tariff, but there will be an additional expense from the last statement. The phase advancing equipment costs a certain 10% of the 100 rupees. So that accounts for your interest and depreciation as explained on the previous video. So to get the annual savings, you probably just get the difference of the savings from the tariff to that of the expenses for your annual expense for your phase advancing equipment. So first, what is the savings that is going to be computed given the change in kVA? So to make this more comprehensive, let's first solve for kVA1. So relating hypotenuse to adjacent in relation to adjacent side in relation to the angle, the trigonometric function is of course cosine. So the kVA here, cosine 36.87 is 800 over kVA. So the kVA must be 800 kilowatts divided by cosine of 36.87, which is 1000. So that's our original KVA. And the other KVA after the correction must be 800 kilowatts divided by cosine of 18.1949, which is 842.1054. The savings in tariff, therefore, savings in tariff. Yeah, because this one is 50 rupees per kVA. So supposedly, we are to pay 50 rupees times 1,000. But now we're just going to pay 50 rupees times 842.1054. I guess we have to complete the decimals. So 1000.0013 originally. Now 50 is just going to be multiplied to 842.1054. So the savings due to tariff must be 7894.79 or point 0.8. This is in rupees. However, we also have the expenses due to the power factor correction. So expenses of, let me just say, the capacitor. So this is savings, right? But you have this is your annual saving, but you also have your annual expenses. So what's the rating? 10% of 100 rupees per kvar. So 10% of 100 rupees per kvar. And the capacitor has a rating of 337.0545. So how much is this? 10% of 100 is 10 times 337. So this is obviously 3370.55 rupees. And this time, this is an expense. So the annual savings must be the difference between the two. So 7894.8 minus 3370.55. So 7894.8. Oops. 7894.8 minus 3370.55. That must be 4524.25. So this is now this is in rupees again. So that's now our annual savings after the power factor correction.